All right, and we are back. I won't throw in another ACDC intro for you guys this time, just because, I'm just trying to get this done and I'm lazy. So, with that, anyway, we'll get going. So, the first circuit that we want to look at is just a very basic ACDC circuit. Now, we're going to go through, we're going to analyze the different components, and we're going to kind of find out what is doing what at each component, at each level, things like that. And then the biggest thing we're looking for is what is our output doing? Um, what voltage do we have? What's our DC voltage? What's our min and our max? What's the phase angles? That kind of stuff. And we'll do a couple of these, and then the next topic we'll have is these guys do have a frequency response, so they're going to have a set of frequencies that they can operate under, and then we need to understand what's going on at those frequencies, with filtering out things like that, um, you know, because not everything's going to run at every frequency. So if we want, we can design it to run at certain frequencies if we just change the capacitors and we follow some of the filtering rules that we've already established. So that's kind of the idea. That's the plan of where we're going to go. So as we get going, like I said, feel free and take time to, as I'm running through these equations and these calculations, I will kind of pause a little bit at the end of it before I reveal the answer. Give you guys a chance that you can pause it without having to rush and get the answers before I get them to make sure you guys are doing them right. Use me as a double check. Obviously, as I'm explaining these and the first time you're running through them, it's going to be some new ideas, new thought processes, but the idea is just the same. Is the math and the theory behind it is the same as what we've been doing. We're still going to be using Ohm's law. We're still going to be using Kirchhoff's laws. All the different parameters. Again, it's just more of an application of the things that we have been learning. So, one of the things that we need to know or to understand is we have kind of a general rule of thumb. This is one of the assumptions that we need to make, and the things that we can get away with now that we're into these AC/DC circuits. So now that we're getting into these circuits with the frequency responses, some of the answers are going to start shifting around a little bit just because the equipment that we have is not perfect. We're not going to get exactly the frequency that we need. The inductors and the capacitors, they may vary a little bit from especially from what they're rated at, and then sometimes they're actually going to vary a little bit as they as you use a part, as you heat up something, very susceptible. These parts are very susceptible to temperature changes. So as things get warm, they're going to change a little bit. If things are cold, they're going to change their values a little bit. So we're going to have some fluctuations on these parts. uh, and then the biggest thing is to understand that that's okay. We're going to have a little bit more variation in this section than we've had before. So, as we get with these values, and that's kind of the thing now that we're into the filters and stuff like that, we're going to see variations on our calculations and our measurements, especially in lab, and especially with the equipment that you guys have. It is not the most accurate stuff on the market. I'll be honest, it's not. You're going to pay lots of money for the really accurate things, and even then, you're still going to see a little bit of variation here and there. But that's okay. We take that into account and we understand, hey, we're going to have a little bit more variation. So honestly, with these ones, 10% and or 10% variation is not abnormal sometimes. And especially with the calculations you guys are going to be doing, because we can't accurately measure that inductor, you could go through and build your test circuit with a known frequency, known resistance values, and go through and see when your voltages line up and things like that. And you can actually go through and calculate those inductor values, as you want going through there. That's one of the ways you could do it, since we don't have a meter for you guys to measure those inductors on. But just so you know that we're going to have a larger variance for error than we've had previously. And it is important that we're still accurate, but just understand that this is going to increase a little bit, and it's fine. We need to just have an understanding that right now we're going to get close enough to the right answer, and we're going to call it good because we don't need to be super exact at this moment. There will be times that you will have to be super exact, but right now, and we can calculate, we can account for all those variables. But right now, we're not going into all the little things that's going to throw our values off. So one of the things that I was getting to is kind of our general rule of thumbs and some assumptions that we're going to make. So in a series circuit, if the values we're adding and subtracting together are are really small comparatively to each other, then we can ignore them, as kind of a general rule of thumb. So in a series circuit, if values that are added together are less than 10, 15, 20 times less than the value we're adding to, we can essentially ignore it, and we can consider it a short for all intents and purposes. So in a series circuit, if the values that are added together are less than 10 times smaller, so basically if they're less than 10, the original amount divided by 10, it's essentially a short. That'll come into play a little bit more when we're talking with our capacitors, because at really low frequencies, they're going to be really, really large, and depending on their orientation, if it's a really, really large value in parallel, we can ignore it, which I'm going to talk about here in a second. And if it's at high frequencies, the reactance for a capacitor is very, 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 very small. So there could be a time where we have a capacitor and its reactance is less than an ohm, and and the rest of our circuit, is 1,000 ohms, a kilo ohm. We're looking at, a mega ohm, things like that. So at that point, we can essentially ignore that 1 ohm resistance because it's not going to change anything, at least with what we can measure. So, it still is there and it still does exist, but we don't have to take that into account in our calculations, if it's less than 10 times the size of what we're adding it to. So it's not going to have that much of an effect. So that's our kind of our rule for a series circuit. So our next one is in a parallel circuit. If the value in parallel is greater than 10 times the value that we're looking at, it is essentially an open. And we can ignore it. So for example, like I said with the series one, so if we had a 1 ohm X of C value and we had a 1 K ohm resistor value, basically what this is going to equal as our impedance total is 1,000 ohms. We're going to ignore the cap, okay? Because at 1,000 ohms with 1 ohm, that's not going to make a big difference at all. We're not even, it's something we couldn't even measure. We're talking about, half a degree, tenths of a degree different in our phase angles, so we can effectively ignore it. So in this one, in a parallel circuit, if the value is 10 times larger, then we consider it an open, okay, and then we can ignore it. So for example, again, if we have 100 ohms of resistance in this, and let's say our capacitor here is 300 kilo ohms at a very low frequency, this is essentially going to be an open compared to that 100. That 300 isn't going to affect this. This guy is going to be 99.99999999999, and if we round it off at 3 decimal places, we're back up to 100 ohms anyway. So, like I said, if it's larger than 10 times what we're in parallel, we can effectively ignore it. This is going to be an open. And if things are 10 times smaller in series, we can effectively ignore them because they're essentially just going to be a short. They're not going to have much of an effect on it. And you'll see that as we go through these, that'll kind of simplify down some of the calculations a little bit, and it makes it really easy to, makes it really easy to solve the circuits when we start cutting out parts of the components and things like that. That, like I said, are not going to affect our calculations that much. They're just going to bog things down. All right, so with those two assumptions in place, like I said, and as we do that, you'll see these coming out. And if you want to, you can include them in your calculations, but just note that it's not going to affect them that much. All right, so the first thing we have is our circuit. So we have, and one of the things that we have to do now is we have to take into account all the resistance of our circuit. So when we hook up our generators, they're listed as 50 ohm internal resistance generator, and that's stamped right on the front of them, like from the one at school. The ones that we have, the little handheld units, those are in the manuals. If it's not given, we just kind of assume about 50 ohms of resistance or impedance from the generator itself. And like I said, we do have to take that into account because sometimes it will play a part. So if we have something down in the 50, 60 ohms for our impedance total, absolutely that RGen is going to steal half the power at 50 ohms of rest of the circuit impedance. But when our circuit impedance is up, around 1,000, 2,000, 10,000, that 50 ohms can effectively be ignored because it's not going to create any major problems for us. But just realize that it is there and we do have to take it into account, just like the winding resistance of an inductor. That's another thing that's going to be, that we have to kind of take into consideration as well. So anyways, we have our generator. We come in through, we go through capacitor 1, which is a coupling capacitor. We go from that into R1. And then from here we branch. And then this is where we're going to bring in our DC portion. So we have R2, we have R3, and then up here, we're going to add in our DC voltage coming in. We're going to split it up between these resistors. Then we come back down here to our junction between R1, R2, and R3. We're going to come off, and then we have a bypass capacitor. So with AC, it's going to basically short out this value to allow it, to change our voltage drop with whatever it may be. And then our voltage out is going to be taken off of the R3 capacitor 2 branch. So the whole idea is we're going to be looking at Rn versus R out. We're going to be solving for these things. So now let's put in some values. So R2 is going to be 430 ohms. R3 is 510 ohms. Capacitor 2 is 5.6 nanofarads. Resistor 1 is 620 ohms. Capacitor 2 is 1.814 microfarads. And our generator is going to be putting out 6 volts peak to peak at 3.994 kilohertz. So basically we were trying to set this thing up to 4 kilohertz. This is as close as we could get it. That's the value we're going to use to calculate this guy. And then what we're going to have is on our DC voltage, we're going to have a plus 13 volts. Now we could add a plus, we could add a minus, doesn't matter. It's going to shift the 0 point of our AC signal. And so now that we have this circuit done, the things we want to look for is we want to find what is our voltage out. Let me get my list. We want to know the voltage out DC. We want to know the voltage out peak to peak with its phase angle. And then we want to know our V out max and our V out minimum. So basically we're identifying how much DC voltage do we have in the circuit, what's our total AC portion of the circuit, and then we want to know what's the max voltage we reach and the minimum voltage we reach after we apply our AC signal on top of the DC signal. Okay, so now that we have this is what we're going to be doing. This is going to require a series of redraws and working on these portions of the circuit individually. So the first thing we're going to do is and I think I'll even change colors on this one. We are going to do our DC redraw first. Does not matter which one we do first. I just usually prefer getting my DC going because that gets my bias, especially in transistors, which you guys will learn next year, is we start with the DC bias first. That tells us how the transistor is going to operate, how a circuit is going to base operate, and then we start adding in alternating signals to it. Okay, so with the DC redraw, we're going to start with our generator, so the positive point of our voltage supply. So this is going to be our plus 13 volts. And then we're going to draw what it's connected to. So the first thing it's connected to is R2. Now it comes to this point and it's going to split. So coming straight down to our ground, we now have R3. And then coming off of that branch, we have a capacitor. But remember, a capacitor is essentially an open to DC. We're going to assume this thing's been on. We're not worrying about the charging constants, anything like that. It's on, it's running. The capacitor has had the time it needs to charge. So we're not trying to figure that out. This is after it's said and done. So once we do that, we essentially have an open from there over to here. So this is where C2 would be. And then coming across here, we have R1, but then we're connected up to another open, which is C1. And then we have our RGen and our VGen, so the generator. So, and then at this point right here, across our R3, this is V out. Okay, so essentially what we're looking at is on our DC redraws, we have the two capacitors that are going to be reading as opens. So the one in open with basically in parallel with R3 is going to have zero effect on the circuit anyway. Doesn't even matter if it's there. The capacitor 1 with this coupling capacitor is making it so we don't have a connection to our generator. So our generator is not going to be in the equation. R1 is not going to be in the equation because it's connected to an open, so it's just hanging out. Capacitor 2, we don't even need to worry about that because it's an open. So what we're left with is just simply our generator for our DC power supply. We go through R2, we go through R3, and we go to ground with our V out right there. So that's all we have for the DC portion. That's the power of the coupling caps, is it blocks DC signals, so then we don't even have to worry about anything that's left over as an open. Now, if things were shorted out, that'd be a different story, but as an open, it's just as if they were hanging out in air against a very, very, very large resistance. Not going to change anything. Okay, so we come out with this. We have our R2, R3 values. Now we just need to find what is our V out DC value. It is just simply a voltage divider at this point. So it's going to be the voltage drop across R3. So we use R3 over R2 plus R3 multiplied by our voltage total. And it's really that simple when we get to it. So let's put some values in there and then we'll give you guys a chance to solve for it. So our V out DC is going to be the 510 ohm resistor over the 510 plus 430. We multiply that by our voltage total, which is 13 volts DC. We run that through our calculator. And again, this is going to be where I'm going to pause for a second, let you guys run through your calculations. And if you need to pause the video, you can. And then once you've decided to unpause the video, or if you just kind of watched it straight, we're going to end up with a total of 7.095 volts. So this is our DC offset of this signal because of how we biased it with the rest of with R2 and R3. So we're going to have 7.1 volts essentially of DC, and that's going to now be our zero line for when we graph this out. Okay, so let's go ahead and put that up here in our answers. So now the next portion that we need to do is we need to solve for our AC part. And we need to find out how much voltage do we have being dropped from our signal, which is 6 volts peak to peak. How much of that is coming across the output? So now one of the things too is when we're looking at these guys, remember that when we talked about the circuit theorems like Thevenin and Norton and superposition and that kind of stuff, we're doing the same thing. We're just looking at each individual power supply first and then going on to the next. So the thing we want to do is when we're solving for our DC portion, our AC portion is going to short to ground. So in this instance, this actually should have looked like this. Because we're only looking at the DC portion. So we take this power supply, we short out the rest, and we solve the voltages for it. Then we're going to use this power supply and we're going to short this power supply and solve all the values and then combine them together. So it's the same thing that we were doing when we talked about superposition briefly, but like with with mesh and all those different things, we're solving each individual portion separately and then we'll combine them together at the end. Okay, so anyway, so that's so that we have the DC portion. Now we have our AC redraw. So we want to look at what is our generator seeing. So again, remember our voltage supply is going to be shorted to ground this time because we're looking at the AC generator. So the first thing that we have is obviously our generator. What is it looking at? What does it see? So we have our gen. That's going to come up to capacitor 1. We're going to go through R1. And then connected at this point, we have just normally our R3. So that takes care of this portion right through there. Now we got to worry about R2 and C2. Well, if R2 is now the voltage generator up here, this is now connected to ground. That means this one can swing down and now it's going to be in parallel with the rest of these guys. So here, and I'll show that as we swing it down just to make it better. So we have our VDC that we've now shorted out because we're doing just the AC portion to ground. So the ground is being connected to all the other grounds. And so now we're left with R3 and R2 in parallel. And then the last portion we have is we have capacitor 2, and that is now also in parallel because it's to ground as well. And then this value here is our V out. So our V out is connected across the entire parallel branch of this circuit. So like I said, this is where everything is coming together. Now we're talking about series parallel circuits with resistors and capacitors. We're going to be talking about filtering. Everything is coming together with these guys. So now this is our circuit for our AC portion. Now we just have to go through and solve and find out what is my voltage drop across this parallel branch. What is the voltage from V out to ground? So one of the first things we need to solve for is we need to solve for our reactance values. So X of C1, X of C2, we need to see what we are dealing with. So remember, our formula to find capacitive reactance is 1 over 2 pi times our frequency times the capacitor. So we have 2 pi times 3994, which is our frequency, times a 1.814 microfarads. We take the reciprocal of that. We get 21.967 ohms for X of C1. X of C2 is 2 pi times 3994. And on that one, it is multiplied times the 5.6 nano. So let me put these back in here, 5.6 nanofarads. R2 is 430 ohms. R3 is 510 ohms. R1 was 620 ohms. Capacitor 1 was 1.814 microfarads, and this was 50 ohms. All right, so our X of C2, that comes out to be 716 ohms. And remember, these are at -90 for their phase angles. All right, so now what we need to do is we need to get our Z total. So we can find the current, so we can find the voltage drop. So the impedance total is going to be equal to, we're going to just label these again as our impedance of the series portion. So I'm going to call this Z series added to Z parallel. So I'm just going to use my ZPT, which is what we've been using this whole semester. So we need to find out what each of these values are. So Z series is equal to our gen plus X of C1 plus R1. Now, let's take a look at these numbers. Okay, first thing that we're going to look at is, well, what is going to affect it? Okay, we have an X of C1 that is 21. We have an RGen that's 50. We have an R1 that's 620. Both of these guys are less than 10 times the other values. So essentially, we can ignore these guys. They're not going to have that big of an effect on the circuit. This RGen might have a little bit bigger effect because it's closer to the 10%. But again, we're going to make a little bit of some assumptions, some generalizations here. But essentially, we can get rid of that value. In my calculations, I did include RGen just because it is so close to this 10 times. But this X of C1 flat out ignored it because it is way, way, way less than the 620. It's going to have almost zero effect on this circuit. Okay, so with that in mind, our Z series is going to be 670 ohms because we're going to keep RGen, we're going to keep R1, and we're going to just, for the sake of this, we're going to remove the capacitance because it's 10 times less. It's essentially a short compared to the 620 ohms. Oh, yeah. Okay, so now our Z parallel total is equal to R3 in parallel with R2 in parallel with the reactance of capacitor 2. So when we come back and look at these guys, what do we have? We have a 510, we have a 430, and we have a 7,000. Okay, again, C2 is 10 times larger than our value. So if we were to go through and solve for this guy, basically what we're going to have is, so if we take the 510 and the 430 in parallel, that's going to be 233 ohms of resistance. Just take the reciprocals of each side, add them together, take the reciprocal of that. That's what this is going to equal up to. If we put that value in parallel with the 7,116, we're going to end up with 233 ohms of resistance. So it's, like I said, it's not going to affect anything whatsoever in this circuit. And so what we're going to do, again, with this value being so high, we're going to treat C2 as an open because it's so much larger than the other ones, it's not going to affect it. So effectively, we're going to cancel this value out. We're not going to deal with it in our calculations. Okay, so our Z parallel total is going to be just simply R3 in parallel with R2. So we have 510 ohms in parallel with 430 ohms. And that gives us a value of 233.298. So just so you guys can see that I'm not crazy and that this assumption is still going to work, this is the value that we're going to be using, is right here. This is the parallel total. But I will show you what this is going to equal if we carried the X of C in there. So we leave X of C2 alone. So we take 510 at 0 in parallel with 430 at 0 in parallel with 7116 at a negative 90. Okay, so again, I'm just going to combine these two guys together because they're resistors and I want to deal with one value. So this comes be the 233.298 at 0 degrees in parallel with the 711.6 at 90. So 7,106 ohms at negative 90 degrees. So now that I'm down to just two branches, I'm going to use the product over the sum, save myself some flip-flopping back and forth between polar and rectangular notation. So we end up with a 233.298 at 0. We multiply that by 7,116 at 90, at negative 90, and then we divide that by the 233.298 minus J of 7,116. This value we need to convert into polar, and when we do that, that becomes 710 or 7120 at negative 88.122. Okay. So now we multiply the 233.298 times the 7116. We divide that by the 7120, and that's going to give us our total impedance for the circuit. And then for the angles, we take 0 plus a negative 90 minus a negative 88.122. So when we do all that math, this ends up being 233.167 ohms at an angle of negative 1.878 degrees. Now, if we compare these two values, we have less than, well, we have what? 1 or 0.111 ohms difference, which is, compared to 233, is nothing. It's not even a drop in the bucket. So this is just kind of going to prove that this is the why we can do this, because this value in parallel is not going to affect this very much. You know, yeah, it's going to be a little bit of current, but it's not enough that we're going to see a difference. And especially with this 1.878 degree phase angle, we're not going to see that at all on our scopes, especially not the ones we have. They are not that accurate. That is well within its accuracy just by itself, which I think it was accurate 2 or 3%. So this is just going to get lost in the noise, and we're going to kind of make a guess, and it's going to be different than what we calculated anyway. So we might as well just save ourselves some work and just ignore that value because it's 10 times larger than any of these in parallel. So once we have that, we're going to go through and we're going to finish solving the rest of the circuit. So we have our impedance total that we need to calculate for is going to be Z series plus Z parallel. So we end up with 670 ohms plus 233.298 ohms. And we end up with a grand total of 903 ohms, 0.298. That is the total impedance of the circuit. So now that we have that, now we need to find our current and find our voltage drops. And then we're going to find our min and our max voltage. So the current is equal to the voltage out, and we're in peak to peak because that's what we started with here. So 6 volts peak to peak. And I forgot to write down that part. Divided by, so we come back down to our current, so it's the voltage, and we are in peak to peak divided by the impedance total. So that is going to be 6 volts peak to peak at 0 divided by 903.298. Now again, we would have this little bit of a phase angle if we were dealing with a capacitor, but we're going to take our liberties a little bit. We're going to make these assumptions, and so we're just going to do this. And also, you can see we don't have a phase angle anymore. We're just back to normal, regular math, even though we have a capacitor in there. So we end up with 6 divided by the 903.298. That gives us 6.642 milliamps. And then our V out is going to be the current total times the impedance of our parallel branch. Okay, so we end up with the 6.642 milliamps multiplied by the 233.298 ohms, and that gives us a grand total of 1.550 volts peak to peak at an angle of essentially 0. All right, so now that we have these two values, we have our V out in peak to peak, and we have our VDC. So I will grab that value from the previous one that we did, so 7.095. So now what we need to do, the last part of this, is we need to find out how are these guys going to be combined together. So to simply do that, what we need to do is, let's look at what our output waveform is going to be. So we have our waveform. This right here is going to be our DC offset, or how much DC voltage we have. So we have V out DC, and then we're going to find our min and our max to be able to plot this guy. So we have our V out max. So what's the most it could ever be? Well, it's going to be this voltage DC, what is it writing on, plus our V out peak to peak divided by 2, because we only want the peak value. So the V out max gives us 7.095 plus the 1.55 divided by 2. So this is 0.775 volts. So we're going to go up and down this. So V out max, 7.095 plus the 0.775. So we're going to have a max voltage of 7.87 volts. And then our V out minimum is going to be the DC level that we're at minus our peak voltage. So we have to take the peak to peak, divide it by 2. So the V out minimum is equal to the 7.095 minus the 0.775 volts. So the minimum we get comes out to be 6.32 volts. So when we come back and look at our graph, our V out DC, this is 7.095 volts, and we're going to have our AC signal writing on it, and our max voltage here is going to be the 7.87 volts, and the minimum voltage here is going to be 6.32 volts. In comparison, to our VN, oops, try and draw these guys somewhat to scale. Anyway, so this is our -6 or our -3 volts. And then this is our +3 volts peak, because we have 6 volts peak to peak. So our V in compared to our V out, we've shifted it up, but we've maintained the properties of our AC signal. So, this is something to where we could have a sensor that we want a sensor to turn on every so often. Maybe we have, for example, a security system where we have an infrared emitter that we want to basically send pulses, and we're going to be watching for these pulses. And if the distances in between these pulses, like if somebody walks through the beam, we're going to see a change in the time. And then that way the system's not constantly on and constantly drawing power. We're going to see the sensor turn on for a little bit, turn on, draw some power, then it's going to shut off, then it's going to turn on, then it's going to shut off. And we know the timing of this, and then we can build our receiver circuit so that it's looking for the signal, but it's looking for it in a time. And if that time gets delayed, that means the beam's been broken and somebody's crossed through the system. Just different applications, because sometimes it's more efficient to use a pulse than it is just a constant signal, and looking for that. And so, we'll get over the 7 volts, the sensor turns on. Under 7 volts, it shuts off. So we have this short period of time where it's actually turned on, and then we have a little bit of time where it rests, cools down, whatever it may be. It could be a very high power laser, and that's how we're controlling the heat, is by pulsing the laser, turning it on, turning it off, which not necessarily good for the laser, but it's something that we could do. So anyway, that's what we're looking for in these circuits, is we're trying to find out what is my DC value, where am I writing on, what is my peak voltage coming out, and then what is my min. Oops, I kind of overlined that one. So we're looking for our peak, we're looking for what's our maximum voltage and what's our new minimum voltage compared to where we were. And then also, as we get into the next step, we're going to be looking at, the phase angles of these guys and making sure they still maintain and follow our rules that we have for, for frequency responses. Okay, so there's that one. So let's go through one more circuit as practice. Okay, so we're going to use the same base circuit. We're just going to change our values up. So let me redraw that guy in there for us. So we have a resistor coming in here, a resistor here going to ground. We've got R2, R3. This is our voltage DC. Coming out from between R2 and R3, we have our capacitor 2 with our output being taken at that point. Coming the other direction, we have R1. We have capacitor 1. We have our Rgen. All right, so let's put some values in this guy. So Rgen is 50 ohms. Capacitor 2 is 633.6 nanofarads. R1 is 91 kiloohms. R2 is 30 kiloohms. R3 is 12 kiloohms. And capacitor 2 is 2.2 nanofarads. We have 2 volts peak to peak coming in on our AC portion at 152.593 hertz. And our VDC is a positive 14 volts. All right, so let's go ahead and solve this. First off, I'm going to solve using the AC portion because, again, it doesn't matter what we do. We just need to solve for both of them. So we have our AC redraw. So we're going to have our generator. So Vgen, Rgen, and then we're going to go into the capacitor 1. This is going into R1. Now remember, our VDC is shorted to ground. So if that's to ground with the schematic symbol, we can bring everything down to where everything is laid out nicer. So R1 is going to be connected into R3 to ground in parallel with R2 to ground in parallel with our capacitor 2 to ground. So, and with our output is being right across there. So now the next thing we need to do is we need to solve for our reactances. So our X of C1 is equal to 1 over 2 pi times our frequency, which is 152.593, and the capacitance, which is 633.6 nano. The X of C2, or X of C1, comes out to be 1646 ohms. And the reactance for capacitor 2, do the same process, only this time we multiply it by the 2.2 nano. And that comes out to be 474,092 ohms. So essentially at this point, we got to look, okay, what do we want to add? What do we not want to add in our calculations? So if we look, we have Rgen, which is 50 ohms. We have R1, which is 91,000 ohms. And so we're going to look at just this portion right here because it's our series section. And so 1,646 is nothing compared to 91. It's well less than 10%. So we can pretty much treat C1 as a short. We can treat Rgen as a short because 50 ohms is definitely not going to make a difference compared to 91,000 ohms. So in this instance, our Z series is equal to simply R1, because everything else we're considering a short, just to simplify this to get an approximation of what we're going to be seeing here. Okay, so then let's also take a look at our Z parallel. So Z parallel, we have R3, which is 12K. We have R2, which is 30K. And we have X of C2, which is 474K. So again, we have 10 times larger than the values in our parallel branch. So this is going to be essentially an open because it's so much larger. And now these, when we're talking about them, we're going to call them a virtual open because they're not an open. They are still there. They do have value. They do have purpose. But for all intents of our calculations, we're not going to use them because they're acting as if they were opens or shorts. So we call these virtual opens virtual shorts because we're only treating them in our calculations as if they're opens and shorts. But in all reality, they are still there in the circuit and they are still going to have some effect, but it's going to be very, 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 very tiny. So in this case, our Z parallel total is going to be equal to the R3 in parallel with R2, and parallel with an open, which is the same as if nothing was there anyway. So we end up with our Z series is equal to 91K. Our Z parallel total is 12K in parallel with 30K. And so our parallel total comes out to be, where's it at? $85.71. So the total impedance between those two resistors is 8,571 ohms. And now, since all we have is resistors, because everything else we're treating as not there, now we can just simply use voltage divider to solve for this guy. We don't have to get into the polar math. We don't have to get into finding the phase angle. We're assuming that these aren't going to have a huge effect, and they're going to effectively cancel each other out, and we're going to be left with a zero phase angle. Okay, so we can just solve for our V out. We can just simply use voltage divider. So we take the 8571 and we divide that by the R1 plus our parallel total, and that comes out to be 99,571. We multiply that by our 2 volts peak to peak. So V out is equal to Z parallel total divided by Z parallel total plus R or Z series, and that's multiplied by our V gen. So our V out comes out to be 0.172 volts peak to peak. So in the very end of this, we're not going to have a lot of AC portion of our waveform. It's going to be very, very small compared. Because if you think about it, we have a 14 volt signal, and depending on how we split it up, it's going to be that value plus our, half of that value. So it's going to be like 80 some odd millivolts. So not going to be much. Okay. So now that we have this value here, and remember this is at an angle of 0 because all we have is resistors. So now we want to look at the DC portion of the circuit. So we have our DC redraw, which we start from here and we short the other power supplies. So we have our plus 14 volts DC comes down through R2 and then down through R3 to ground. And then if we look at our circuit, we have a capacitor here at C1 and capacitor at C2. So to the DC portion of this, these two are going to be opens. So R1 is connected on one side and then open to the other, which basically is not going to do anything. It's an antenna at this point. And C2 is an open, so it's not even going to be there. So this is all we have for our DC portion. And then we're looking at our V out, which is going to be the voltage drop across R3. So our VDC is going to be equal to the resistance of 3 divided by R2 plus R3, that value multiplied by our voltage DC total. So to calculate that, we get 12K over 12K plus 30K, multiply that by 14. So our VDC comes out to be 4 volts. Now we need to find the V out max and our V out minimum. Basically the 2 points on our sine wave on our AC portion riding on this DC value. So remember, D out max is going to be our voltage, or the voltage of our DC, plus half of our peak voltage. So plus V out peak to peak divided by 2. To find the minimum, we're going to take the DC value it's riding on, and we're going to subtract out half of our peak to peak value. Just the peak value is what we're looking at. So V out max is equal to 4 plus 0.086. So that gives us 4.086 volts. And our V out minimum is equal to the 4 minus the 0.086 volts. And that gives us 3.914 volts. So it really is that easy and that simple. We have the ability to go from our AC portion and look through the whole circuit, see what's doing, make some assumptions as needed. If things in parallel are greater than 10 times its values, then we can treat it as an open. If it's in series and it's 10 times smaller, we can treat it effectively as a short, which then is just going to simplify everything down. So, in this circuit, we got rid of, a third, half the calculations needed, and these values aren't going to change that much. If we were to go through and incorporate everything, we would see like a V out peak to peak of, maybe instead of 172 millivolts, like 169 millivolts or something like that. So we're not going to see that much change. And so like I said, with that makes it really easy and honestly better to calculate these circuits. We can start whipping these out pretty quick. But know that we are using, a little bit more of approximations, and so the values are going to shift just a little bit, but they're still going to give you in the ballpark with everything else that we've been doing. So anyway, so that's the basics about AC/DC circuits, how to calculate them. So basically the idea behind this is we're biasing our circuit to set up the DC parameters, and then we're plugging in an AC signal, and we're going to analyze it and find out, okay, how much of that signal is getting to the output? Okay, now that I have these two pieces, my DC writing, or my DC level, which is now my 0, and I'm going to vary up and down by my AC signal, which is our peak to peak. How much am I going to vary by? Well, that's what we solved for there. We're going to cut that value in half if it's in peak to peak. Or if it's just in peak, that's even better. That's one less calculation we have to do. But all we're looking for is how far up is it going to go above our DC value? How far down is it going to go below our DC value? And that gives us our output. The idea behind this really is this is the precursor to amplifiers. This is how they're all going to be set up. Is you're going to have a DC portion, which is going to bias the transistor, which is going to turn it on, partially turn it on, get it ready, and then you add in an AC signal, and then that's going to be amplified through it based on our output. So, like I said, this is the precursor to transistors. So it's very important to understand that it's just a simple DC circuit, and it's just a simple AC circuit. And then we have to take into account, okay, what is my relationships of all these guys? Do I have values that are 10 times larger? Do I have values that are 10 times smaller? And that will kind of help you make adjustments and, kind of get a real quick picture without having to go through pages and pages of calculations to solve for these guys based on every little single component. Now you can, I'm not saying you can't or that it's wrong to do that. You can go through those, and that's going to dial in your answer. So you're going to exactly what you calculate is exactly what you measure. And, at times you need to do that. But, a lot of times in the field, in industry, things like that, you don't really care if you're at 5.2 volts or if you're at 5 volts. So you kind of some of these little tricks and hints that you can do. You can make these assumptions, and you can remove some of the detail because for what you're doing, it doesn't matter. Another example is tools like if you're tracing digital signals, and this is one of the things you guys will learn next semester as well. But a digital signal, if it's considered a high or a 1, it has to be over a certain voltage, and I believe it's somewhere around 3.3 volts that it has to be above. So between 3.3 volts and 5 volts, that's considered a high or a 1. So I mean that's a huge range. And so if we're calculating stuff and we're coming up between 4 volts and 3.5 volts, well, that's not going to matter. That's still well within the range of what the high needs to be. And even then, that's a huge signal loss, considering a 5-volt signal. But the idea is we can get close to these values, and that's going to be good enough. It's like the joke I made between the engineer and the mathematician. Eventually, close enough gets you there. You don't ever have to actually be right on to earn the prize. You just have to be close enough to reach out and grab it. And that's what we're doing here. Is we're kind of showing you guys that you have the options to get close enough, and that is just fine. And then there are times that yes, you do want to be 100% accurate. Um, we're showing you all these different techniques, these different ways, different methods, things like that. So anyway, so that is the AC/DC portion of this week's lecture. I'll get this video uploaded shortly. I do have the introduction all ready to go, and yep, just what I thought. My AC/DC video got flagged for copyright, so I'm going to have to go back through and edit that one. Makes me sad because I was hoping to keep that introduction. Anyway, I will get this video uploaded and we will go from there. And this one won't have any issues because there is no problems with the copyright because it's my voice. So anyway, enjoy that. The next video will be the frequency response based on these guys. So now that we've been talking about filters, these guys have an operating frequency. So if we run them above or below a frequency, it's going to start attenuating the signal just like we had in the filters. And that's the other types of signals you're going to see is like, okay, I want to have this, this biasing network, and I want it to work at certain frequencies. But when I get above or below that, I don't want to amplify those signals because I don't need those signals. Maybe they're going to interfere with something later on that's operating on those frequencies or things like that. And so this is kind of one of the precursors to of filters and amplification is I only want it to work at certain ranges. I don't want it to work for the whole spectrum of everything. And this is how we're going to calculate where is those points going to happen. So anyway, hopefully, if you guys have any questions, you don't have any questions, that'd be great. But if you do have questions, as always, please feel free to get a hold of me. Any ways you need to with the Zoom meetings, via text, email me, call me, whatever you need, and I will be able to be around to help you guys out and answer your questions for you. And anyway, that's all I have for this video. Hopefully you guys have learned something.